In the last couple of videos, we started with an equation in rectangular coordinates, and we found a polar equation that had the same graph. Now we're going to go the other way. So I'm starting with this equation in polar coordinates, r equals 2. Now, one way I could do this is just say, oh, I know that graph. That's a circle of radius 2 centered at the origin. I know how to describe that in rectangular coordinates. That should just be x squared plus y squared equals 2 squared, which is 4. Okay? But I want to see how we could do it more algebraically, trying to use these conversion formulas. Because this is going to sort of serve as an example of some strategies that we'll use in some more complicated things where we maybe don't know ahead of time what the graph looks like. Okay, so you'll notice over here I don't have r or theta by itself, so I can't just replace r with something, and there aren't any thetas anyway, but if I had a theta I can't just replace it with something the way I can if I have an x or a y. But I do have an r squared. So what I'm going to do is I'm going to take this equation and square both sides. So r squared equals 4. Now, in general, when I square both sides of an equation, I'm losing some information about the signs of things, right? And so it's possible that I'm introducing extraneous solutions. We saw when we were solving trig equations and we squared both sides, it was necessary to check because we might have something that was an answer to this squared equation that wasn't an answer to the original equation. However, while this did introduce some additional algebraic solutions, r could equal plus or minus 2 now, graphically it didn't change because the graph of r equals negative 2 is exactly the same circle as r equals 2. So these two equations, even though they have different algebraic solutions, have exactly the same graph. But now I can replace r squared with x squared plus y squared is equal to 4. All right. Now again, with this example, I know the graph. If you know the graph, you can just use the graph to get that. But we're going to have plenty of examples where we don't just know the graph, and so we're going to want to be able to use some algebra. Okay. Let's take a look at, let's say theta is equal to pi over 6. Okay. Well, again, in my conversion formulas, I don't have a theta, but I have a tangent theta. So I'm going to take tangent of both sides. Tangent of theta would equal tangent of pi over 6, which of course I don't have memorized. I know sine and cosine, but I have to draw my 30, 60, 90 triangle. Oh my goodness. Pi over 6 was 30 degrees. Tangent is going to be 1 over root 3. So we've got tangent of theta is 1 over root 3, which I can rationalize. So that's going to become, times root 3 over root 3. So we're going to have tangent of theta is root 3 over 3. But now I can replace tangent of theta with y over x. So y over x is root 3 over 3. And I'm just going to get this in standard form by multiplying over by that x. Y is root 3 over 3 times x. Now that makes sense because I know that theta being constant was giving me a line through the origin. This is a line through the origin. Its slope is just that tangent. It's tangent of pi over 6, or root 3 over 3. Kind of cool. Okay, so let's try another. Let's start with one where maybe we're not familiar with the graph to begin with. Let's say I had r is equal to cosine of theta. Okay. Well, I don't have just an r, and I don't have just a theta, but if I were to multiply both sides by r, let's see what would happen. I would get r squared is equal to r times cosine of theta. Okay. Now r squared, I can use this formula. R cosine theta, that's just x. I'm liking this. Okay. Now, I do need to be careful. When I multiply through by r, it's possible that I added extra solutions. Okay, so we don't divide by variables because we don't know if that variable might be 0, and we don't want to lose solutions with that variable being 0. We generally don't multiply by variables because we could be introducing solutions. Clearly, r equals 0 is a solution to this equation because there's an r on both sides. Okay. Now, r equals 0, that corresponds to just a single point. So we sometimes do allow ourselves to work with that because often that single point was already part of the graph. And it was here, because there are certainly values of theta that would make cosine of theta 0, which would make r 0. So in multiplying both sides by r, I did not introduce any extra points to my graph. Okay, so now I can say this is x squared plus y squared is equal to x. Now, if all I wanted was an equation, I'm done. That's a perfectly valid equation for what we have here. What I'm going to do is, it looks to me like this might be a circle, because I see x squareds and y squareds being added together. I'm going to see if I can get it in standard form and confirm or deny that suspicion that this is a rumor, or that this is a circle. So I'm going to subtract over that x. So we'll have x squared minus x, and I'll leave a little bit of space, plus y squared at this point is equal to 0. And we're trying to make this a perfect square. So we're trying to make it look, remember, like x plus d squared, which would be x plus d times x plus d, which is x squared plus 2 copies of dx plus d squared. So I've got 1 copy of x squared, that matches. The number of x's that I want to have is 2d. The number of x's that I do have is negative 1. So d would have to equal negative 1/2. Therefore, d squared would equal positive 1/4. I want to add a 1/4 here, which I can only do if I also add it to the other side. But then I know that that factors. That's x plus my d was negative 1/2, so x minus 1/2 quantity squared, plus y squared equals 1/4. And so now I can see, yes, that is a circle. It's centered at 1/2 comma 0, and its radius is the square root of 1/4, which would be 1/2.